mixed integer programming is. And you will find that different applications that you work with and power systems, mostly unit commitment or battery optimization, or any problem where you have to make a decision, or you have variables that cannot take continuous values, but rather integer values, is where mixed integer programming can be very useful. It can be very useful. So let's see. Let's see. Uh, uh, Take the same formulation we had before, right? We want to minimize a linear function subject to linear constraints h and n-dimensional vector x, right? What we're going to add here is that the vector x of variables is such that one or several of its components have to be integer. So let's say that you have a vector of dimension 10, and all the components are continuous except one, which is integer. That makes the problem a MIP problem. So as long as we have one variable that has to take integer variables, that makes the problem a mixed integer programming problem. Okay. The functions, however, remain linear, MILP, mixed integer linear programming. But the difference is that some variables now are integer. As a side note here, there is nothing that keeps you as a user to restrict that a variable is integer or binary. And we'll talk a little bit about that. So when a variable is integer, and I want to repeat this because it's important that it's understood. If a program is a linear programming problem, you have a constraints. For example, x1 has to be greater than 0 and less than 10. If x has to be between 0 and 10, and the problem is a linear programming problem, then x can take any value between 0 and 10, 0, 0.1, 9.5, whatever. But if you make the variable integer, then x can only take integer values. It can be 0, 1, 2, 3, 4, and all the way up to 10. It cannot take values like 8.6. Okay? All right. So I think it's clear now that mixed integer linear programming, MIP, is the same as LP plus the integrality constraints that we talked about. Okay. Now, to reinforce what I just described, we're gonna do a small example that I hope you enjoy and you find intuitive. It's a very simple example where we want to manufacture some furniture. We want to manufacture some furniture. So on the left, you have a stool, a little bench. On the right, you have a chair. Okay. And there on that little chart, we have the money we expect to make on each of that. So if we sell one stool, one bench, we make $10. If we sell one chair, we make $11. Okay. Now we have to, let's write this as an optimization problem. First, we have to decide how many of each we want to make. How many stools do we make? How many chairs do we make? So the quantity of chairs and the quantity of stools is something to which we assign variables x and y. And these variables are going to be integer. Why? Because we cannot make 8.5 chairs. We either make 8 chairs or 9 chairs, but we cannot make a fractional value of chairs or stools. So the variables that represent the number of stools and chairs have to be integer variables, right? Okay. Now, since we know what money we make out of this furniture pieces, we can write our objective. We want to maximize the money we want to make. We want to maximize our profit. And then, of course, since we know how much we get for each unit we assemble, the objective is going to be 10 times X plus 11 times Y. $10 for every stool we make plus $11 for every chair we make. That is our objective. Now, what constraints do we have? Well, that will depend on a couple of things. And this simple example, of course, is going to be the material that we have available and also the man hours, the workers that are going to help us assemble this furniture together. So when we assemble a bench, a stool, or a chair, we need the seat component. We need the seat part. So each piece of furniture requires one seat, and we only have 10 available, right? We also have, well, that translates into a constraint. So for every chair that we make and every stool that we make, we add one seat to the formulation, and we only have 10 seats available. So we cannot, between chairs and stools, add up to more than 10 seats. That's a constraint that we have. Next constraint, long pieces. The long pieces are what we use to make the legs and the furniture in the back, I think. Yeah, and the long ones. So we need four legs for a chair and three legs for a stool, right? And we only have available 36 pieces to make those legs, right? So we know that because we need three legs for a stool and four legs for a chair, what would that constraint look like? I wish I could ask the audience. I'm sorry, I mean, I don't have that interactive capability, but I think it's clear. I think it's clear that three legs per stool plus four legs per chair is the total number of legs that I'm going to have, and the total number of legs cannot exceed 36 because that's what I have in inventory, correct? The same goes for the short pieces. I'm not going to repeat this one. It's the same thinking, the same type of formulation. That's another constraint, right? So here we have an optimization problem where we want to maximize our profit subject to constraints. And of course, something important that I left, I didn't say is the labor, right? We need 4 man-hours to do a stool and 2 man-hours to do a chair. So we have one worker, let's say that we have one worker, and we have that worker available to us for only 35 hours, okay? So we have materials, we have labor, and we have our profit function for this problem. Okay, what is the solution to this problem? We're not going to do this here. If we solve this problem with Gurobi or you do it by hand, you will find that the solution to this problem, the way it's written, is 4.5 and 5.5. If we solve this problem as a linear programming problem, the solution is 4.5 stools, 5.5 chairs. Okay, that mathematically might make sense, but if you look in reality, we cannot make 4.5 stools and 5.5 chairs, right? Because we cannot make fractional values of a chair. We cannot make half a chair or half a stool. So this problem, it's missing a constraint, it's missing a condition, and the condition that is missing is that both x and y have to be integer, right? We have to solve this problem considering that both x and y have to be integer variables. Okay, let's see how this looks from a graphical point of view. And this is something that you're going to find pretty useful when you start working with optimization models. If you can draw for a problem that has, well, it doesn't have a n-dimensional variable, and this is a simple example because we have a two-dimensional problem where we can draw all our constraints. All our constraints that you see there are in the blue lines, and if you take the intersection of those constraints, it's the shaded area that you have here on the lower left corner. That shaded area is our feasible region. If we find the vertex in that region that optimizes our problem, it has to be an integer variable. So what I'm saying is, if you look at the problem the way it is now, nothing keeps a continuous variable from being taken inside the feasible region. When we add the condition that x and y have to be integer, that restricts the feasible region to be only on those points that you see on that grid, right? So if you place the integer values, which are the points inside the feasible region, we know that one of those points is going to be the solution to our problem, correct? So how will we do this? How will we do this? In this case, the problem is so small that if I took, for example, all the points that are inside the feasible region and along the boundary of that region, and I start trying one by one on the objective 10 times x plus 11y, I could try all of them and then keep the one that provides the highest objective function. That will be our solution. So that doesn't seem so hard, right? But let me show you how hard this can become, and I'm going to do that relating to to a problem that I think you're mostly familiar with, and then we're going to go back to this. Okay? So let's take for a second a super fast computer at Oak Ridge National Lab, a computer that can do 200 petaflops. That is 2 times 10 to the power of 17 operations per second. That's a really, really fast computer, okay? And then let's see how long it takes that computer to process 0, 1 points, binary points in n dimension. To put that in a more digestible way, take a unit commitment problem. If you have one generator, the only decision you have to make is whether the generator is on or off. Let's take one generator and one time interval. So on this time interval, this generator is either on or off. If we take two generators, it's a little more complicated because both generators can be off, both can be online. The first one can be on, the second one off, the second one on, the first one on. So we have four options. The more generators you have, the more combinations to try you have. If we take one interval and n generators, we have 2 to the power of n combinations, different combinations of generators. If we want to look at each of them separately with this supercomputer, let's see how long it takes. If we have 10 generators, we have 1024 combinations, right? 0, 1 points to check. And that will take for this computer no time, 0 seconds, right? Because we're dividing 1024 by 2 times 10 to the power 17. Now, if we increase the number of points, let's say we have 60 points. Now we have more combinations to check, right? We will have 1.15 times 10 to the power of 18. That will take 6 seconds to this super fast computer. Let's say that we increase now just a little more. Let's add 10 more points, 70 points. Well, that is 1.18 times 10 to the power of 21. That will take 1.6 hours to check. That is already a little bit of a struggle. And if we go just, let's go all the way to 120 points. That's a really big number, 1.3 times 10 to the power 36. That will take 210 billion years. So we cannot just enumerate. That will take forever. So we need a way to systematically reduce the search of the space that we want to consider. And that's something that I'll explain in a second. But basically, what I want to convey to the audience now is that with combinatorial problems where you have many decisions to make and you start doing all these permutations, doing a brute force enumeration works for a very, very small problem. So for a realistic size problem where you have I don't know, and I'm going back to my unit commitment where you have hundreds or thousands of generators, where you have a long time horizon, 24, 48 hours, then it's impossible to do an enumeration. The number of combinations is just astronomical. Okay, how we solve a problem then in practical terms? Let's go back to the problem of the stools and chairs, and let's stay with the mathematical side of it. Okay, we have a problem where we want to maximize this function subject to those constraints, but we know that x and y have to be integer. Okay, let's start first by assigning our maximization function 10 times x plus 11 times y to a variable z. Okay, c is going to be the value of our objective function. We want to know what the value of that function is. What's the best we can do for that function z? Okay, for that number c. Okay, we're going to find this function f of xy to be 10 times x plus 11y. That's our objective that we want to maximize. Okay, so let's start with a wild guess. Let's say that we decide to do nothing. I'm not going to manufacture any chairs, any stools, and see what happens. Is that feasible? Yes or no? I am asking the audience so you can write down your answer. It's x equal to 0 and y equal to 0 a feasible answer? It is feasible because if you take x equal y equal to 0, and you plug that in any of the constraint, it will satisfy that. 0 is less than 10, 36, 41, and 35, and 0 is integer. However, if you plug 0, x equal to 0, and y equal to 0 to the objective, the value is 0, right? And the objective will be 0. We have not manufactured any chair, any stools. We don't make any profit. It is feasible, but it's not really the best we can do. We can do a lot better than this. So we know that the optimum value of C, which is C star, where we want to go to, has to be greater than 0. We have to have a profit. I mean, even if we make one chair, one stool, or one of each, or just one, that's going to be better than doing nothing. But we do have an absolute lower bound. We know that we have to be at least 0. We have to be greater than 0. That's a lower bound of our objective function in this maximization problem, okay? We call 0 an incumbent solution, and that's something important that if you are going to work with optimization, is something that you're going to become familiar with. Incumbent means the best feasible solution that you know at a given point in time. So 0, 0 is our incumbent. It's not very good, but it is our incumbent because we don't know of any other solution that is feasible. So 0, 0 is feasible. The objective value is 0, and that is our incumbent. That's what we know. Okay, that's our lower bound. That's our lower bound. We cannot do worse than that. What about an upper bound? Is there a way to estimate a number that we cannot do better than? Let's try to find an upper bound now. An upper bound. Uh, we'll try to find an upper bound for our uh, uh, objective function, and for that, we are going to use the constraints to do that. So let's take the first constraint. Let's look at it. X plus y is less than 10, right? If I look at that constraint, I can say that if I make no chairs, the number of stools cannot be more than 10, right? And if I make no stools, the number of chairs cannot be less than more than 10, right? So if you look at that inequality, x plus y less than or equal to 10, you can conclude that both x is less than 10 and y is less than 10, correct? If you multiply those two inequalities by 10 on the x factor and 11 on the x factor to mimic what we have in the objective function, right? We're doing this multiplication here in the last row to construct what we have in the objective. So if you do that and then you add up these two functions, you end up with 10 times x plus 11y, which is our objective function, cannot be more than 210, which is 100 plus 11 and 10. That means that our objective cannot exceed, by constraints, 210, right? So let's add that. We know that our solutions have a value that cannot be more than 210. So let's that as a low as an upper bound. Okay, so what we know so far is that our objective function cannot be worse than 0, but it cannot be better than 210, right? We know that our objective has to be constrained to that range between 0 and 210. Okay, so that's our upper bound. That's what we call an upper bound. Sorry, let me take a sip of water. So now, let's go back to our incumbent solution and let's see how good it is. We know it's not very good because we're not making any chairs or any stools, and we're pretty sure that we can do better than that. If the continuous problem solved to 4.5 and 5.5, there must be an integer solution that provides an objective that very likely is between 0 and 210. So this solution is really not very good. A way, and this is something else that you have to become familiar with, a way to quantify how good a solution is given by what you see normally in optimizer logs as the mid gap. So the MIP gap is a relative difference between the bound and the incumbent. Formally, the MIP gap is defined as the best bound minus the incumbent divided by the incumbent. That relative difference is multiplied by 100 to get in a percentage value. In this case, because our incumbent is 0, the current gap is, well, it's infinite. Plus infinite is undefined. And normally our gap is undefined where our incumbent is we haven't really computed one or is not good at all. So we will improve that in our problem. Let's do better. Let's do better. A gap of 0, on the other hand, that's a question for the audience. If you can reduce that gap to be 0, that will mean that the incumbent and the best bound that you see on the chart are going to be exactly the same. And in that case, we have found the optimal solution to our problem, right? We are going to try to do that. So together, a bound and the incumbent, uh, uh, when they have the same value, that means that we have reached the solution to our problem. Okay? So let's try to improve the bound and the incumbent solution for this problem, so that when we do that, our goal is to see what is going to happen next on the animation. We want to reduce the bound to go down, and we want to push the incumbent to go up, so they meet each other on the optimum solution of this problem. Okay, uh, let's walk again this path slightly differently on the chart of the problem, and let's see if we can improve the upper bound. Our upper bound is 210. Let's see if we can improve such upper bound. These integrality constraints that we have create a challenge for the problem. So let's do something. Let's remove them. Let's remove them for a second. Okay, I'm going to remove the integrality constraints, and we're going to solve this problem. If we solve this problem, when we remove the integrality constraints, what we're doing is something that you will see often referred to as LP relaxation. LP relaxation means that you're taking a MIP problem, you are relaxing a condition, in this case, the condition of integrality, so you end up with LP, with an LP relaxation, which is just a linear programming problem, and then we solve that problem. When we solve this problem, as you recall, the solution was 4.5 and 5.5, and that's the dot that you have in the chart. If you plug that solution on the objective function, you will have 4.5 times 10 is 45 plus 5.511. I think that's something like 105. Let's see. There it is, 105.5. Right? So if you take 4.5 times 10 plus 5.5 times 11, you end up with 105.5. So the solution of this relaxation yields 105.5. We know that our problem cannot be better than 105.5. Why? Because if the original problem has integral conditions and remove those integral conditions, we have less restrictions. We can find the best objective, which is 105.5. And then when we add back the integrality conditions, that's going to make the objective go lower, but it cannot be better than 105.5 if we add more restrictions, correct? So 105.5 is an upper bound for our optimization problem. I hope that part is clear. This is called the root relaxation because we haven't branched on any node yet, and what we will see what that is later. When we solve the original problem and we relax it, by relaxation I mean remove the integrality constraints, that's what we call the solution of the LP relaxation. Okay? So the less restricted problem, the relaxed problem, yields 105.5, and this is an upper bound for us. So this is nice because now we know that before we thought, okay, we cannot do better than 210, but now we have more realistic expectations. We know that we cannot do better than 105.5. That's our best bound, okay? So that's a big step. We cannot do better than that number. Okay, now we improve the bound of the problem, the upper bound. What about the incumbent? We're still left with an integer solution that is zero chairs and zero stools. So can we improve that? Okay. To do that, we had removed the. I'm sorry, I went the wrong way. Can we improve our incumbent? Let's try to do that. Let's try to guess a good solution. Let's try to guess. I'm sorry, a good solution based on what we know. Uh, when we guess a solution, a feasible solution based on what we know, that's what we refer to as heuristics. Okay? And in this particular case, I would ask again the audience to take what we had originally, which was 4.5 and 5.5, which was the solution to the LP relaxation, right? And if you recall the shape of our feasible region, common sense will tell us, okay, if we take those two numbers and we round them from below, that will get us to the next integer solution, which is feasible, that sits inside the feasible region. So if you make 4.54 and 5.55, that solution is feasible because if you take 4 and 5, 4 and 5 will satisfy all the constraints that we have here. They're both integer. And if you plug them in the objective, you're going to get, let's see, 40 plus 55, that's going to be 95. So that will be our incumbent. Incumbent means best feasible solution. Since we're maximizing and our previous incumbent was 0, the objective function was 0, and we're maximizing, the next incumbent, which is 4.4 and 5, yields a value of 95, which is greater than 0, and this becomes our new incumbent. This is our new current best feasible solution. Boom. And this is a lot better. So now we know that our problem at least has a solution of 4 stools and 5 chairs, and we know that this problem cannot be better than 105.5. That's our bound of the relaxation. Okay? This is great. So now let's compute for this problem what the gap is. So recall before our gap was indefinite. We couldn't even compute a gap. Now our gap is 11%. Ideally, the gap, as we talked about a few minutes ago, the best gap that we can achieve is 0. I mean, if we can match the bound and the incumbent, we know that we cannot do any better. Here, very likely, there is room for improvement. So let's go back to our problem. We know we know that. Oh, I'm sorry. Let me take a sip of water. Going back to the difficulty we had before we derived that point using heuristics, we recall that the fractional solutions are bad, right? So when we solve the relaxation, to this problem, this is what we got: 4.5 and 5.5, and that is the red dot that you see there. So although that is in the feasible region, it's not on top of one of those dots that we have there, so it's not really feasible because it's not integer. So is there a way, if we can find a way to add a constraint that only cuts this red dot from the feasible region, that would be great, because if we did that, perhaps the relaxation that we will be left with can yield a problem for which the solution is integral. Let's try to do that. So basically what I'm saying is, if we can find an inequality that cuts off the solution of this LP relaxation. Basically, I want to cut away that red dot, but I want to leave all the points in the grid. Okay, so let's see if we can do that. Cuts basically, and you will see that also with Gurobi. When you solve a problem, after you run the problem, you will see that Gurobi automatically adds cuts that do not remove away the feasible region, I mean, as far as integrality constraints, but it will remove parts that make the LP relaxation tighter to remove points such as 4.5 and 5.5. Gurobi does that automatically, and you can see it in the stats in the log. We will see that in a few minutes. So let's try to derive a cut. And all of this we're doing today is just for you to understand how the solver works. This is something that normally you wouldn't have to do yourself. So let's try to derive a cut to remove that point that we don't like. Okay, so there's a way to do this with some algebraic manipulation. We have this optimum point, and now what we're going to do is we're going to find, we're going to add the restriction that the problem has to be integer, right? That's what we want. For that, we're going to add some integer slacks to this inequality constraints that you see there, and they are going to become part of our optimization problem. So we have slacks S1 through S4 that we add to each of our inequality constraints to make them equality, and they become part of the variables that we are using to optimize, to maximize this function. Now, we're going to take this problem, and we're going to go through some stages to generate a cut. First, we're going to do an aggregation. Basically, an aggregation is we're going to take the two constraints in this constraints that we have for which the slacks are 0. So if you take the first and third constraint and you replace on them 4.5 and 5.5, you will find out that S1 and S3 are 0. Okay, so we're going to write it here. Okay, and now we are going to combine these two constraints. We're going to eliminate X. Okay, and then we're going to rewrite Y as a function. I mean, I mean, we're gonna clear Y of the factor 2, as you can see there, divide everything by 2, and then we're going to derive the chi by weakening this constraint. How do we do that? We're going to take the equation that we just derived, and I'm sorry if this part is going to go a little fast. You don't need to worry about the details. This is just to show you how a cut, not so much important how do we derive the cut, but what happens when we have the cut. If we weaken this equation by rounding from below the coefficients of the slacks, right, you're going to see that Y minus 3/2 plus 1/2 less than or equal to 11 divided by 2 becomes what you see there. So that 1.5 that multiplies S1 becomes 2, right? And the S3 becomes 0 because we're running from below, right? Then this is less than or equal to 11 divided by 2. If we take this number now, and we strengthen, considering the fact that all our variables are integer and the slacks are integer, that means that the right-hand side has to be integer. So we can take 11 divided by 2, 5.5, and make it 5, because we know it has to be integer. So it cannot be, I'm sorry, it cannot be 5.5. Okay, if we take now that constraint that we just created, right, and we add it to this problem, by replacing an S1 by X, right, we have produced a new cut. And the cut is what you see below. Y minus 2 times 10 minus X minus Y less than 5. That equation that you see there that results in 2X plus 3Y less than 25 is a new inequality that we have created for this problem that hopefully will cut that fractional value away. Okay? And you can do this as an exercise after the presentation. But again, this is something Gurobi does in the background, but I just want to show you where the magic comes from. So let's see what happens with this new equality we just derived. We have that point there that we don't like because it's fractional on the LP relaxation. Now we're going to add this new inequality. And that new inequality that you see there, it's the red line that you see on the graph. That red line is just below the point, so it will cut off that 4.5, 5.5 point from the graph. So it's removed from the problem. So it cuts the optimal solution of the LP relaxation. When I say LP relaxation, it's the problem that doesn't have integrality constraints. So solving the new tighten relaxation should give us a better solution for the upper bound on S, and the upper bound on Z, the upper bound on Z is the LP relaxation. So let's see what happens. Boom, let's solve that problem. There it is. We solve this problem, and the solution is 5 and 5. And this is without considering the integrality constraints. So as you can see, that cut made the feasible region such that when we find the solution on a vertex, the vertex is going to be a point of integral values, x equal to 5 and y equal to 5. If we replace that value in our problem, the optimal solution is, well, the upper bound is going to be 10 times 5 plus 11 times 5. That's 105 for the solution of the problem. In this case, what happens? We know that our solution is 105 for the LP relaxation, right? That's the upper bound. But we also know, what else do we know? What do we know about the incumbent? You see the upper bound went from 105 to 105.5 down to 105. So we improve a little bit the bound, but we also know that the solution to the relaxation is 5.5, which is integer. And because it's integer and it's better than what we had before, which was 95, 105 becomes our new incumbent. And because the incumbent and the bound have the same value, we have found the solution to our problem, because in that case, the gap is equal to 0. There, okay? So the solution of this problem is 5 chairs and 5 stools. I'm going to repeat one part that is key. We found a solution to an integer problem solving an LP relaxation. Okay, and that seems counterintuitive, so I'm going to spend a moment talking about that again. If you solve an LP relaxation, chances are that the solution of the LP relaxation will have variables that have continuous values, fractional values. However, by adding cuts, in some cases, like in this example, the cuts are such that you can create a new updated feasible region on which the vertex of that LP relaxation lies in a corner that has integer values. And that's what happened here. That vertex, which was our new upper bound, happened to be also our new incumbent, in this case, 105. The gap, of course, is 0, because the difference between the incumbent and the relaxation is 0. They have the same value of 105. Okay, so let's revisit this example and do a more I'm going to talk more about more things that are done within Gurobi to improve the solution of the problem. In this case, we're going to look at the pre-solved stage. Okay. So first, we're going to look at this problem, and we can see if we can tighten the formulation without removing any feasible points. Okay. Let's see if we can do that. So something we didn't do before, but we're going to do now in a second pass of analysis of this problem, is take advantage of things that we can exploit. For example, if you look at the third constraint, the fourth constraint, 4x plus 2y less than or equal to 35, is there something obvious that you see? One thing that we can notice in this constraint is that because the variables are integer, x and y, and they're both multiplied by even numbers, we know that the summation of those two variables multiplied by even numbers has to result in an even number. So that constraint can be made a little more compact by turning down 35 down to 34, because we cannot achieve a value of 35 with the conditions that we have on the left-hand side, right? And I'm going to repeat this. So pay attention to the rightmost line. It's going to move slightly to the left, right? So that helps. That helps because if we do that, we make the search space a little smaller. In our case, this will not change. In this case, although we have made the feasible solution, feasible space a little smaller, it's not going to change the solution of the LP relaxation because the vertex on which it is not really affected by what we have done. How would we combine the ideas that we have talked about to solve this problem? Uh, how do we do this? How can we use some sort of enumeration, systematic enumeration, to improve the solution time of a problem like this? We're going to go back to this example just to present some ideas that in this case they're not going to make a big difference because it's a small example, but in most cases, that's what we use. So let's take the solution that we had of the relaxation, which was 4.5 and 5.5, and let's see what we can do with it. Okay? Let's take this problem, right? And we know that the root node, if you recall, the solution of the relaxation is 4.5 and 5.5, right? And that's what we have at the root node when we haven't done any branching on the problem. And I'm going to talk about what branching is. Root node is when we haven't branched on any of the integer variables. We know the solution to our problem is 105.5, right? And that's for 4.5 and 5.5. And we know that if we round those numbers from below to 4 and 5, our best incumbent is 95, right? That's what we have when we start. So something that we do in Gurobi, and most solvers do this, is we keep track of what our solution is and what the value of the relaxation is, 1.5, and then we do we look at the values that we have achieved, and then we decide okay, we're going to take we have a strategy to pick in the variable to do this, but in this case, let's pick x. We know that x cannot be fractional. X has to be integer. So what we do is, to the original problem, we're going to add a constraint saying, okay, because x is 4.5, then I know that x cannot be more than 4, right? So I'm going to add that condition to the problem to force on the original problem a condition such that x cannot be more than 4. So it doesn't achieve that value of 4.5. If I solve that problem again, then x is going to be equal to 4, y is going to be 5.8, and you can try this on your own, and the new solution is going to be 103.8. Okay? So you see our bound became is a little lower, but we still have a fractional value on y. So what do we do now? We repeat the same process. We can do a new branch for y such that y cannot be more than 5. So we force y to be less than or equal to 5 to force it to not be 5.8. And when we do this, boom, look, we find an integer solution, x equal to 4, y equal to 5, and the objective function is 95. In this case, this incumbent is not better than what we had originally of 95, right? And that's something we found ourselves, if you recall, when we rounded off the numbers from below. So we found the same result here of 4 and 5 by doing branching, right? So this is our incumbent. Okay, to find the best bound, we have to do the other leaf nodes, So let's try now to do the branch on the other side. If you go to node 1, where y is 5.8, we can do another branch on which y has to be greater than 6. And then with those two branches, the branches on node 1, 1 and node 1, 1, 1, 2, we are preventing y of taking that fractional value of 5.8. If we do this one, you can see that, well, y now is 6, yes, but now x doesn't have an integer value, is 3.7 on that branch, 1.2. And the relaxation is equal to 102.7. So this doesn't really solve our problem. Let's go back up. Here, well, we'll have to keep branching, right? We will have to keep branching because we don't stop branching until we find an integer solution. In this case, from node 1.2, I would branch on x to have x less than 3 and greater than 4. And that will be another branches. Okay? So let's see how this looks like. Let's see how this looks like. If you recall, if we take x equal less than 4, because we don't want it to be 4.5, x less than 4 means that we're going to optimize only on the area that you see as red. That will be our first node that you saw on the branch and bound graph, right? If we optimize on y less than 5, which is another node that we have, node 1, 1, that's it's a smaller area that you see in the red area. And so we start constraining the area on which we're doing the optimization by branching. And this yields one of the points that we found in node 1, 2, if you recall. If we go now back to the graph, let's branch at the root node, but now on the other side of x. So instead of branching, we did already the branch on x less than 4. Let's branch now on x greater than or equal to 5. If we solve that problem, so you see we're taking the original problem on the right and we're just adding that condition that x has to be greater than 5. And we solve the relaxation, we're going to find that x is equal to y and the objective function is 105. Because this solution is integer, we have found a new incumbent. Why? Because this incumbent is higher than 95. And also now we can take the bound and update the bound, and we have found a solution to our problem. This disqualifies all the other nodes that we have because our gap at this point at this node is equal to 0. So this is another way of finding a solution to the problem by branching on the variables. In this case, it was fairly straightforward because we have only 2 variables and there's so much branching that we can do. This is the branch and bound technique. Okay. All right. So let's go back to the problem and show you where the solution is. It's right there. This, as you can see, it's a lot of work, and I don't expect you to take your unit commitment problem or if you have any problem you're working with and do this by hand. You can do it once, twice, or whatever times you want. I mean, to learn the technique, I find it quite fascinating. But Gurobi will do this for you. Okay. So Gurobi takes care of all of this, but it's important that you understand, because sometimes once you have an understanding of these basic techniques, you can see where Gurobi spends time doing heuristics, doing cuts, and sometimes if more time than if you see that a lot of time is spent doing cuts, maybe we can do something to improve the cut generation or the heuristics. I mean, we can take advantage of a particular nature of a problem to steer the solver in one direction or on the other. So Gurobi will do all of this. Gurobi does pre-solve, cuts, heuristics, branch and bound, and more. You just have to give the model to Gurobi. You just have to worry about creating your model and passing it to Gurobi. Okay. How do we terminate an algorithm now, regardless of how you do this? If you recall, we talked about that relative measure between the best bound and the incumbent, right? You have the incumbent is the best feasible integer solution, and the bound is the solution to the relaxation. Once you have the relative difference between them, You can tell Gurobi, I want to terminate the solver if that relative difference is less than certain percentage, or if that absolute difference is less than a certain number. So you can tell Gurobi, I want you to finish when the difference is within 1%, or the difference between the best bound and the incumbent is 10. Most people use the relative MIP gap, but you can also use the absolute gap if it makes more sense to you. I would say that what I've seen in some ISO applications, some market applications, a gap of 1 or 2% seems to be reasonable, because the lower the gap, I'm sorry, the lower the gap, the more nodes you have to explore, the more time it will take to find a solution. The solution will be better, but you will need more time to get to that solution. So there's a trade-off between the quality of the solution you want and the amount of time you're willing to wait. As I said, I've seen that in some ISO applications, a gap of 1% seems to be reasonable to solve a real-time application that has to solve every 5 minutes, every 15 minutes, and a gap that provides a solution that maximizes the profit for market participants. I mean, it seems to be a reasonable gap. You can experiment with this number. Uh, you can also terminate Gurobi with a time limit. You can say, well, I want to terminate if the gap is within certain value, relative or absolute, or if the time spent crosses a certain, let's say if I spend more than 1 hour, I can terminate. So you can provide all this termination criteria, and whenever you meet the first one, the solver will terminate, and you can experiment with this. You can also pass the number of nodes. So in some cases, some users, they don't care so much about the time or the gap. They care more. They have an idea of the problem size. So because they have an understanding or an idea of how big the problem is, they say, okay, if I explore at least 100,000 nodes, I know that I've explored the portion of the problem that I'm interested in, or the size of the problem that I'm interested in, and then I can terminate the algorithm or the number of feasible solutions. I mean, there are different ways to terminate the algorithm, and you can see this in the reference manual, or you can ask me after the call for more information. Okay, how are we doing with time? Okay,